Bad Bugs, No Drugs, The Emerging Crisis of Antibiotic Resistance by Linnea, Schultz, and Lapid.
What is antibiotic resistance? Antibiotic resistance occurs when an antibiotic has lost its ability to effectively control or kill bacterial growth. In other words, the bacteria are resistant and continue to multiply in the presence of therapeutic levels of an antibiotic. When an antibiotic is used, bacteria that can resist the antibiotic have a greater chance of survival than those that are susceptible. Susceptible bacteria are killed or inhibited by an antibiotic, resulting in a selective pressure for the survival of resistant strains of bacteria.
Why we chose this topic. On September 2nd, 2016, the FDA ruled that starting September 2017, 19 antibacterial agents, including triclosan and triclocarbon, will be banned from being sold in the marketplace. Manufacturers did not demonstrate that the ingredients are safe both for long-term daily use and more effective than plain soap and water in preventing illness and the spread of certain infections, the FDA said in a statement. We wanted to investigate the findings of the FDA, as these have been hotly contested in the scientific community and media, and determine the comparative rate of resistance between the antibacterial and non-antibacterial agents. While other lab research articles we read explored antibiotic resistance, we did not find any that compared both consumer antibacterial agents and pharmaceutical antibiotics to plain hand soap.
Lab overview. In our lab, we measured the rate of resistance of E. coli bacterium in the presence of 3 different pharmaceutical antibiotics, ampicillin, streptomycin, and tetracycline, to compare these to antibacterial hand soap and plain hand soap. In order to test the resistance, we poured agar plates and streaked them with E. coli, and placed the corresponding antibiotic pellet or soap on each plate and measured the zone of intermission, or ZOI, daily for each plate for 5 days. The ZOI is the innermost blank ring around the antibiotic pellet or soap where the bacteria have been killed. We placed 2 pellets or soaps on each plate, recorded as Zone 1 and Zone 2, and on each day, we recorded the decrease of ZOI in millimeters in order to see the trend in data over time. We also took note of the efficiency of these products in killing the E. coli bacterium in order to assess if antibiotic products were more effective than plain soap over the same period of time.
Hypothesis. Our initial hypothesis was that both the plain hand soap and the antibacterial hand soap, but the plain hand soap more so, would produce bacteria that were less resistant than those using the antibiotic pellet plates, while still managing to achieve around the same efficiency in killing the bacteria.
Materials. In our experiment, we used the antibiotic pellets ampicillin, streptomycin, and tetracycline. The antibacterial hand soap was soft soap antibacterial hand soap with moisturizers, active ingredient, benzalkonium chloride, and the plain hand soap was method Sweetwater hand soap, which specifically stated it was antibiotic-free. The rest of the materials can be seen here.
Procedure steps overview. Our procedure consisted of 5 different parts. Pouring plates, day 1. Adding the antibiotics, day 2. Adding the liquid soaps, day 2. Recording the data, days 3 through 7, and disposing of plates, day 7. Note: because we were working with dangerous bacteria, we took the safety precaution of thoroughly washing our hands and bleaching down the lab station and equipment before and after each day of conducting this experiment.
Pouring plates, day 1. Measure 20 grams of nutrient agar powder using electronic scale and pour it into an Erlenmeyer flask. Place flask with 500 milliliters of distilled water onto the hot plate heated to 235 degrees Celsius until water boils, then place on low boil for 15 to 20 minutes. Open plates and fill each with 20 milliliters of agar broth. Allow plates to harden and flip upside down. Repeat steps for a total of 31 plates, 6 for each antibiotic or soap, and 1 for control that does not get any antibiotic or soap added. Place in fume hood for storage.
Adding the antibiotic pellets, day 2. Streak each plate with E. coli. Using sterilized forceps, place 2 of the corresponding antibiotics into the agar, a minimum of 20 millimeters apart. Each pellet will be recorded at either Zone 1 or 2. Your plate should look as follows. Repeat these steps for the rest of the antibiotic pellet plates.
Adding the liquid soaps, day 2. Now moving to the liquid soaps. As we did not want either the antibacterial or plain hand soaps to dry out and skew our data, we cut off the ends of sterile cotton swabs and pipetted 30 microliters of soap onto each cotton swab, then placed it in the agar for the corresponding plate and zone, as we did for the pellets.
Recording data, days 3 through 7. Using a ruler, measure the diameter of the ZOI in milliliters for each plate. Observe if the bacteria in the control plate are growing as expected. Once you have recorded the measurements for the antibacterial soap and the plain hand soap, pipette 30 microliters of corresponding soaps to the sterile cotton swabs.
Disposing of the plates, day 7. Pour 10% bleach solution onto a plate to kill the bacteria. Place the plates in the fume hood for 30 minutes. Repeat for all plates.
Data. In order to show the rate of decrease of the ZOI, here is the data table of the first and last day of measurement of our plates. Using these averaged, we averaged the rate of decrease of the ZOI between all the plates for a soap or antibiotic. We found that tetracycline had the highest rate of resistance with a decrease of 29.07% of ZOI. Next was streptomycin with a decrease of 12.775%, then ampicillin with a decrease of 8.52%. The antibiotic hand soap had the second lowest rate of resistance at a decrease of 7.16%, and the lowest rate of resistance was the plain hand soap with a decrease of 4.58% ZOI.
This graph of averages shows the data from the table and clearly indicates that the pharmaceutical antibiotics had a higher rate of resistance, as their ZOI had a much greater decrease compared to the commercial soaps.
In these graphs, we compared each element to the plain hand soap in order to show the remarkable differences in the rate of resistance. Even though the hand soap was about as effective as the other agents, it showed the least amount of resistance over time.
Conclusion. Our hypothesis was supported that the plain hand soap and the market antibiotic hand soap showed less resistance in terms of their daily ZOI measurements. In this regard, we support the FDA's findings and agree with the 2017 ban on antibacterial agents being sold in hand soaps and other cleaning products, as they appear to do more harm without substantial benefits.
Discussion. We added 30 microliters of liquid soaps to their plates each day and did not add to the pellets, which may have affected our data. If we conducted this experiment again, we would use a wide variety of commercial soaps, both antibacterial and plain, in order to compare the relative rates of resistance and efficiency as well.
Significance to the medical field. Antibiotic resistance is an emerging crisis in the medical field, and if left unchecked, our arsenal of antibiotics may dry up, leaving us in a pre-antibiotic world. This resistance crisis is attributed to the overuse and overprescription of antibiotics. The CDC has found that 1 in 3 antibiotic prescriptions are unnecessary, and if continued, in 2050, antibiotic resistance will kill more people than cancer and diabetes combined. The time to act is now, before it is too late.
Acknowledgements. We would like to give our utmost thanks to our mentor, Claire Bonasai, for helping us draft and revise our project and for being a role model. We would also like to thank our teacher, Dr. Hebe Kelly, for providing us with lab equipment, lab space, and constant motivation. We would also like to thank our parents for their love and dedication.